So far, our study of differential equations has been focused just on exponential. So exponential growth, growth without bound, right? Growth without a limit. We know the graph of an exponential starts out really slow, has that moment where that explosive growth then happens, and then we're on growth without limit. And so yesterday your homework was based on where exponential growth comes from. Exponential growth comes from calculus. It comes from the separation of a differential equation where you have dp dt as a constant multiplier times the population itself. So you start with that, which leads to the PERT equation of P equals P sub 0 e to the kt. So that was the whole yesterday's thing. The other kind of growth is what we're going to talk about today, which is called logistic growth. So what's the difference? Do you guys know? Yeah, growth with a limit. It starts out behaving like an exponential function. So it starts out with a slow rate of growth and then an explosive rate of growth, and then eventually it reaches its ceiling or its maximum and it won't go any further. That's because the differential equation is formed differently. Okay, it's not, doesn't just look like the exponential. It has a what's called a limiting factor. So if we're relating this to our devotion earlier today, God's love for us, God's grace in our life is not like this. It does not reach a limit. It does not level off and say, okay, I've given you enough love in your life. I've given you enough grace in your life. That's it. That's all you get. Thankfully, we do not have a relationship with God that's like that. So this is what a logistic differential equation looks like. It's dp dt equals kp. So very similar in start, but it has what's called the limiting factor. And it's 1 minus the value of p divided by a new constant called m. Okay, so this thing right here is called the limiting factor. And when you recognize it in a differential equation, you know that you're going to have a ceiling to that function. And the variable, the constant variable m, is the value of the max. So when you perform separate and integrate onto this, it develops for you the logistic growth equation. We are going to take the time, because we have a block day, to develop that by separate and integrate. Once we've done it, then you can choose to just memorize the end result, and that will be fine. Okay? Okay, so this is the development of the logistic growth equation using separate and integrate. So we've got dp over dt equals kp 1 minus p over m. All right, when I separate that, what goes where? What has to be on the left side and what has to be on the right? Okay, and so dp would be over the p. it would also be over the 1 minus p over m. The other side would be the k dt. Okay, m is a constant, and it will be helpful to you, I think, if you get rid, the fraction where we've got p over m, if we do something to quote-unquote both sides so that we can have that not be a fraction. It's just a little cleaner to work with. So what's the algebra there so that we don't have to work with that m? Okay, if I multiply the whole thing by m, that's not going to do it. So I multiply the denominator by m. Yeah? Okay, so I'm going to multiply the denominator by m, which means I have to do it on the other side also, but it's just a constant, so that's fine. And so I'm going to distribute. So I'll have dp over p times m minus p. So I distributed that m past the p and into the parentheses. That leaves me with k over m, which is a constant, dt. Okay, now I can integrate both sides. K and m is just a constant, so I can pull k over m outside of my integral, and I'm left with just dt. But let's think about the left-hand side. How am I going to integrate what's on the left? I'm going to need partial fractions. Okay, so because m and m minus p is a factored equation. So this would be a over some p plus b over another m minus p, and the whole thing has the dp on it still. And so we want to figure out what those partial fractions are going to be. So let's just focus on this left side for a minute. Okay, using our partial fractions that we learned from before, I'm going to multiply the first term by m minus p, and I'm going to multiply the second term by p over p. And so I will end up with, bless you, a times m minus p plus b times p equals the original numerator, and the original numerator happened to be 1. So we've got am minus ap plus bp equals 1. Okay, keep in mind, what in there is a variable? P is the variable, okay? And so, for me, it helps me to, say it's not just 1, but it's 1 plus 0 p's. So then I can match up am is the constant that matches to 1, and negative ap plus bp has to be equal to 0. So am equals 1, and negative ap plus, negative a plus b has to be equal to 0. I'm trying to solve for a, and I'm trying to solve for b. So what could you tell me about a? What does a equal? 1 over m. Okay, what will b equal? Also 1 over m. All right, so my integration by parts now becomes 1 over m over p plus 1 over m minus p dp. And on the other side, we just still have k over m dt. So what could you factor out of the left-hand side? Sure. Let's factor out 1 over m. That just leaves me with 1 over p plus 1 over m minus p dp. And I have k over m on the other side. All of this is algebra. What have I pulled out of both integrals? I pulled out not just m, but 1 over m. So what could I do to get rid of that? Yeah, if I multiply both sides by m, which is a constant, yay, I don't have it anymore, which is going to make my math that much easier. All right, we're ready to integrate. So we have the natural log of the absolute value of p plus the natural log of the absolute value of m minus p equals kt plus c. This is a good time for us to find c. Well, I could put these two together. The natural log of the absolute value of p times m minus p, put those together with multiplication, equals kt plus c. Now, this is a good time for me to find c. And what we usually do when we want to find c, we set t to be equal to 0. And what will we set the population equal to? And p will equal p sub 0. All right, so we'll see where that will get us. So if t is equal to 0, then c is equal to the natural log of the absolute value of the initial population times the max minus the initial population. That's our c value. Okay. So, yes, that was my next thing. Yes, we can get rid of the absolute values because we know that what's in there is always going to be positive because the population will always be positive and the maximum is always going to be greater than the population. Therefore, that will always be positive for sure. All right, so we have the natural log of the population times m minus the population equals kt plus our c that we just found, which is the natural log of the initial population times the max minus the initial population. So now we're going to apply an e on both sides. Oh heavens. Guys, gotta catch me. Now I need to look at my notes. No, me.
Okay, what did you do?
My antiderivative was not right. Slightly. What did I do wrong?
Oh, negative.
I forgot the chain rule.
Oh,
Heavens. Because the natural log of m minus p, I did too. Okay, so that just changes all these to a minus. I just need to follow my notes a little bit more closely. But then it changes this. Do a slash. There you go. I'll fix it because I can erase easily. You guys. I should know better than that too. Then I got it. All right. So this is a minus due to the chain rule. So this would be, come on, p over m minus p. This would be p sub 0 over m minus p sub 0. that will be P over M minus P. Okay, now we can E both sides. Okay, now we'll use E. E on that side, E on all of that side. Yes?
Why don't you do the afterlife?
Okay, the population is going to be positive, right? We don't have negative population.
Does it have to be population?
Yes, this is yes, yeah, this is defined. This is the growth of a population. Yeah, P stands for. So it has to. It's never going to be less than 0. Okay, so this is going to clean us up quite a bit for us. So we'll just end up with P over M minus P equals e to the kt. Can I do all of this? Are you comfortable if I do all of this at the same time? Like that? Is that okay? Okay. All right. Next step. We just need to get this into the form where P is by itself. Okay? No, there's different math we can do. Okay, all right, so we're going to reciprocate the equation because we've got fractions on both sides. So take the reciprocal, m minus p over p, that's reciprocal of that, m minus p sub 0 over p sub 0. And then what about the reciprocal of the other one? Okay, I could do 1 over e to the kt. What would be another way to write that? Beautiful, let's do that. E to the negative kt. Okay, now let's focus at this side. I can make that a common denominator. So I can say m over p minus how much? 1. We're really close to having p by itself. What do I do to both sides now to get p by itself? Add 1. Okay. Now how am I going to get this p by itself? Reciprocal again. Sure. You're going to do the same thing. So p over m equals. Now this time I can't just flip everything because I have addition. Right? In reciprocals, if it's an addition, you can't just take the reciprocal of each addition piece. You got to do 1 over. That would accomplish the exact same thing. Yep. We'll end up with the exact same thing, kt plus 1. And now how do we get our p by itself? Multiply by m. All right, so p for the population is m over m minus p sub 0 over p sub 0 e to the negative kt plus 1. And that is called the logistic growth equation. All right. Do you have to memorize this? And the answer is no. I mean, do you have to memorize this process? No. But then you're going to have to memorize the answer, the result. So how does that help? Okay. Let me show you how you're going to need to recognize this. Let's do this. This is called logistic growth. dp equals 100 over 9 e to the negative 0.01t plus 1. All right, so an example of how you would need to use that result would be the simple case right here of just matching up term to term and being able to tell me something about this population. Okay? So you should be able to identify the value of the maximum of the population. You should be able to identify the growth constant of the population. You should be able to identify the original value of the population, okay, the p sub 0. And so it's really just a term-by-term matching. Now it's pretty clear that the maximum of this population is going to be 100. Okay, it's also clear that the growth constant of this population is negative 0.01. Oh yeah, because it is the negative of k. So yeah. Okay, the negative of the negative. Okay, now p sub 0, you're going to have to do a little work. All right, we know that m minus p sub 0 over p sub 0 is supposed to be equal to 9 in this case. We know that the max is 100, so 100 minus p sub 0 over p sub 0 works out to be 9. And then you do the algebra on that by cross-multiplying. So 100 minus p sub 0 equals 9 p sub 0. Add p sub 0 to both sides, that's 10 p sub 0. So p sub 0 is 10. So that's a sample of how you might match up the values. Now, that's an easy one because it's already in P form. It's a little tougher if it's in its differential form. So let's look at that. All right, so something like this, a population growth rate is modeled by dp dt equals 0.1p minus 0.0004p squared. Identify m, k, and p sub 0. Okay, this is a little harder. Now we know this is logistic because it's not just kp. Just plain old kp would be per. This is not kp. So we know it's logistic, and so we need to make it look like, we need to rearrange this into logistic form. So we need to make it look like dp dt equals kp times 1 minus p over m. So we need to do the algebra to make what we were given look like the form that we need. In other words, we have to factor. So what could we factor out so that we've got something factored out and then it starts with 1 minus blah, blah, blah. Okay, not just p, but we're going to factor out 0.1p. Okay, so that's going to be dp dt equals the factored 0.1p out, leaving me with 1 minus. Okay, could you please factor out 0.1 from 0.0004? Okay, 0.004p. Now that is still not quite in p over m form. Change it into a fraction. Okay, so dp over t is 0.1p, 1 minus, okay, what is the fraction for 0.004? Okay, it's 2 over 500, which is 1 over 250. Okay, all right, so this is going to be 1 over 250th of p, which is basically p over m. You could also say it's p over 250. So once you've factored, then it's easy to identify the m, the k, and the p sub 0. So m is going to be what value? 250. K is going to be what value? Okay. 0.1. Okay, now p sub 0. You have to be given something else in this equation to be able to get you all the way to your p sub 0, because you can't tell. There's no p sub 0 in this equation. It has to be something either you're given or you're given some other population where you can work backwards to find the p sub 0 like we did last time. Okay, one or the other. But I'm going to give you the p sub 0 for this one. Given p sub 0 is 28, create the growth equation. So you have two choices at this point. If you've memorized the growth equation, then all you got to do is drop the numbers in and you have it. If you have not memorized the growth equation, did not memorize, you can always go back and separate and integrate. And do it the wrong way. But, you know, at least you have something you could do.
Wait, so are you going to do this problem that we currently have?
Yeah. Okay. All right, so P equals. So we want M over M minus P sub 0 over P sub 0 e to the negative kt plus 1. And so this would be 250 over 250 minus 28 over 28 e to the negative 0.1 t plus 1. So you just got to clean that up. $250 over, it didn't work out nice, 111 over 14 e to the negative 0.1 t plus 1. All right, there is your logistic model from that differential equation. All right, final question based on this problem, and then we're done for the day. When was this population growing fastest? Right, when was this population growing fastest? Okay, I want you to think about the graph of this equation. Okay. Where does it have the steepest slope? Okay, where is this population growing at its fastest rate? Okay, it's going to be right smack dab in the middle there. Do you know what happens there? Specifically about that graph? Has it, okay. Well, it's not necessarily vertical tangent. Okay, it's just steep. It's not vertical. Any other ideas? The concavity changes, exactly. Okay, yeah, which is also a point of inflection. So that place is where the concavity changes from being concave up to being concave down. So this is a point of inflection. So how do we find points of inflection? Okay, set the second derivative equal to, all right, well, where's my first derivative? I was given, all right, I was given the first derivative, and so we were given dp dt to be 0.1p minus 0.0004p squared. So I just need to find the second derivative, which will be 0.1 minus 0.0008 p. And then I set that equal to 0. And so p is equal to negative 0.1 divided by negative 0.0008, which works out to be 125. And so what that tells you is the population was growing the fastest on the 125th day of its existence, is where the growth of the population was at its greatest. And it's all because of that, having a point of inflection right there. Okay? That is when. Sorry, yes. Population. You're right.
So that's the highest population.
That is at that population the growth rate is happening the fastest. So then, yeah, plug 125. Let your calculator solve that though. Back into the 250 over 114 e to the negative 0.1 t plus 1. So what I would do on my calculator is I would do the graph like this, and I'd throw that horizontal line there at 125, and let the calculator determine that point for me. Yeah.
Is it always like the point of inflection, like the T, always the half of the maximum population?
Usually, yeah.
What is T equal?
Well, it depends on what your. I don't know. Yeah, T is the time that's happening.
I don't know about that or not.
Oh, I know. I don't have my calculator out. You can. Bobby, I don't know the answer to that. I'd have to look into that a little bit more and see, because I would think that would be affected by the initial population as well.
Or is this big graph a magic like the cross
Not no, because this isn't halfway, right? Because it would be between 28 and 250. That's not 125 isn't halfway.